Okay, one little thing I neglected to mention in the last video is the inside of your cathode ray oscilloscope has to be a vacuum. Otherwise, the electrons would hit into the air particles and get scattered. So we need to be a vacuum. It's actually, in fact, why a lot of CROs end up not working in schools, is because as soon as the seal around any of that breaks, you just hear a little pop, and the air rushes in, and your CRO is never going to work again. Okay, what we want to look at next, yes, it's important because it might come up in the exam how this works, but it's more important that you know how to use this in experiments. Now, it'd be nicer if we were in school and able to look at some cathode ray oscilloscope screens, but we're just going to draw some here. So this is our first example, and for all these cathode ray oscilloscope screens, there's little options on the front of it that we'll get into a little bit later in another video. But essentially, you can set the scale almost on the X and Y axes of the screen. Okay, and what we just say is, okay, what is the each little segment worth on the X axis? So you can see on our X axis here, between there and there would be a centimeter, or sometimes called the division when it comes to these. And we're just saying that the sensitivity or the scale on the x-axis is 2 volts for each of those divisions. So you might see this written as 2 volts per division or 2 volts per centimeter. But either way, we're just saying that that little gap there on the x-axis is worth 2 volts, and we've gone for the same on the y-axis, so the y sensitivity on this. It's something you can change on the front of the cathode ray oscilloscope, so you can change it if you've got bigger or smaller currents. We're also saying that the time base is off. We'll explain what that means when it's on later, okay? So, based upon that, let's say across our kind of horizontal deflection plates, okay, our x-axis, we have an input voltage of 0 volts to deflect them, and across our y we have 6 volts. So based on that, the little dot on our screen, it's not going to be moved left and right because we've got 0 volts across the x deflection plates. The y, the vertical deflection plates, we have 6 volts, but each of these divisions is worth 2, so there would be 2, 4, and what we would see on the screen would just be a stationary dot of light 3 divisions up. Okay, we're going to use the same scale for each of these. So now the Y, the vertical deflection plates, we have 0 volts across them. We have -4 on the X, the horizontal deflection plates. Each of the divisions is worth 2, so there's -2 volts, and there's -4 volts. So what we would see on the screen would just be a little dot, 2 divisions to the left of the center. Okay, for the next ones, pause the video and try it yourself and try and work out where the dot would be. So our next one, we have X as being 5 volts and Y as being -4 volts. Okay, so X is 5, so there's 2, 4, 6. So 5 means it'd be 2.5 divisions, because each of those divisions is 2 volts. Y is -4, so those combined together would produce a dot 2 divisions down and 2.5 divisions to the right. Now realistically, if we had those voltages, we just use a voltmeter to measure them. Where the oscilloscope comes into its own is when we have voltages that vary with time. Because if we try and measure them using, say, something that has a digital readout, or even something that has a little needle that swings backwards and forwards, it's just going to move too fast. In fact, the needle will just sit there and kind of quiver. The meter will read just different values all the time, and you won't really be able to get an idea of what's going on. So what we have here is a sawtooth voltage, okay? Because if you look at the shape of this graph, it kind of rises and falls like the teeth on the blade of a saw. The Y we're going to just keep as 0 for now. And if we look at this, our signal starts off with -10 volts here. So our dot is going to be 1, 2, 3, 4, 5 squares, which is equivalent to -10 at the start. But as time goes on, that gets less negative. So this little dot is going to move from here, and then it's just going to move across to here, then to here, then to here. And at this point, that dot will have moved all the way across to there. it then gets positive, so it's going to move more to the right. So 2 volts, 4 volts, and it's just going to move all the way along here to 10 volts, at which point it goes back to minus 10 again, and it'll start back over here. Now, if the time period for that kind of one sweep is very slow, you will see a little dot moving across the screen slowly. However, if we speed that up, it can get blurrier and blurrier and blurrier, and eventually what the human eye will see is something that looks just like a line moving, or well, not even moving across the screen, it just appears like a line, because your eye is too slow to pick up that movement. Now, we can then use this type of input on the x-axis to investigate more what's happening on the y. So here we have a little conjunction of two waves that are time varying. So you can see the x one is our sawtooth from the previous one, but now our y is sinusoidal, okay, going from -6 up to 6 and back and forth and back and forth. So if we just look at this, starts off at -10, and at the same point y is 0, which means our dot will be here. By the time it gets to 0, okay, so it won't be affected left or right, you should see that this is kind of back to 0, the equivalent point. And then by the time it gets over here, it's back to 0 again. So we're going to get points there and there, but in between times, it's not quite lined up right, we're going to get a point that is 6 volts in the y, which is 3 up, and in between there and there, we will get one that is 3 down. And what that does is our line is sweeping, our dot is constantly sweeping left to right, but the input on the y setting is causing it to sweep up and down at the same time, and we end up with a waveform on our screen. So this allows us to view alternating voltages much more easily than any other method. Okay. From that, I can see that the peak is 3 divisions, therefore it must be a 6 volt maximum peak. Okay, difficult one now. They will not ask you a question like this in the exam, but based on those two signals, what would the screen look like? Okay, pause it and have a little go, and then we'll talk through it. Okay, let's just start at the start. Good place to start from. If we go to -10, at the start here, the voltage on the X is 0, but it's 6 volts on the Y, which means it's going to be 3 squares up. By the time we get to this point on the X, it's +10, so it's going to be all the way out here, but no deflection on the Y. When X returns back to 0, so it's not sweep left to right at all, this is then -6, which will bring us 3 down. And if we go to this point, on our Y is 0, but the X is -10, which will bring us out to here. And then we're back to the start again, and it just repeats that. And in fact, what we get with these is that dot will sweep out an oval kind of shape and constantly go round and round and round. And in fact, if both those were 10 volts, we would get a circle, essentially.